In the previous video, we talked about the linear regression equation, and we say that interpretation of the linear regression equation depends on the purpose. We talked about one purpose of the linear regression equation, which is the descriptive purpose. In descriptive context, we talked about two descriptive models. One is the linear conditional mean model, and the other is the linear projection model. So the descriptive model is useful for describing how the random variables are related in population, but descriptive analysis is not causal analysis. And in a lot of situations, we want to figure out the causal relationship between variables or among multiple variables. Descriptive can be useful, but it's not causal. So consider an example where Y is the COVID-19 cases per 1,000 population in a randomly drawn state in the United States. And let X be dummy variable for states with a Republican governor. So X equals 1 if the randomly drawn state has a Republican governor, and X equals 0 otherwise. And suppose that the conditional mean of Y given X can be described in this way. Suppose this is the true conditional mean model of Y given X. So EY given X is 22 plus 6.7X. And the coefficient for X is positive, is 6.7. What's the interpretation for that? The interpretation is that states with Republican governors have on average 6.7 cases per 1,000 more than states with a non-Republican governor. So what's the interpretation for that? Interpretation, states with Republican governor on average have 6.7 more cases than other states. Cases per 1,000. Than other states. So that is a useful fact to know. That's kind of interesting. But does this mean that the governor's political party affiliation cause more COVID-19 infection? Does it or does it not? Well, the answer to that question may be yes, maybe no. But we cannot tell, we cannot conclude what the answer is just from the conditional mean model. We're going to need a causal model in order to answer this causal question. So how do we use the linear regression model, linear regression equation, and attach causal interpretation to it? In order to attach causal interpretation to the linear regression equation, we are going to need a story. We're going to need a causal story. And the story is important for attaching any causality to the coefficients. In that story, this equation should be how Y is generated. You should be committed to the story that this is how Y is generated in the real world, how Y is generated in the population. In particular, this equation describes X x1 to xk are factors that contributes to the generation of y, and u should also be factors that contributes to the generation of y. So in particular, u should represent all the omitted factors omitted from these observables that also participate in the generation of y. So you should be committed to say that when these factor values are given, the value of y is generated according to this equation. So that would be the story that you should be ready to tell before attaching any causality to the model coefficients. Now, with that story in mind, once you have a story about how y is generated, if x1 can theoretically be changed while holding the others not changed, holding the others and including observable and unobservable factors constant, then beta 1 can be interpreted as the causal effect of 1 unit change of x1 on y. In the COVID-19 and the Republican governor case, you don't have any of the other x. You only have one x, which is the party affiliation for the governor, but you also have the u. U would, if now in that equation, if you want to attach causal meaning to beta 1, you're going to need a story that tells people why you think the party affiliation of the governor is affecting y. And what are the other important factors besides party affiliation that also participate in the generation of y? Okay, is it possible to hold the other factors constant when you change the party affiliation of the governor? If that is possible, and if that is the thought experiment you are imagining for saying that party affiliation of the governor causes COVID-19 cases, then beta 1 can be interpreted as the causal effect of party affiliation on the cases, on the number of cases. So when you set up a linear regression equation with the causal purpose in mind, the u now represents real things in the world. U now is not just a mathematical concept that's defined to be the difference between some other random variables. Instead, U now represents things that actually exist in the real world. And therefore, in a causal equation, when you treat this linear regression equation as a causal equation, U has real world meaning, and it does not necessarily satisfy either mean independence or zero correlation. So in a causal equation, these two mathematical relationships between U and X are not necessarily satisfied. Of course, this mean independence and orthogonality could be helpful when we are trying to estimate the betas. When we try to take this model to data and try to estimate the betas. But they do not necessarily hold. You're going to have to argue for them based on your understanding of the world or understanding of the problem that you are solving. So mean independence and orthogonality could be helpful for estimation, but it's not required for attaching causal meaning for this on these betas. And they're not even necessary for estimation. So we'll talk about other ways to estimate the betas without assuming these conditions. So causal models attach real world meaning on the error terms are no longer by definition orthogonal or mean independent with the x variables. And in causal models, the betas can be interpreted as the causal effects. So what is a causal question? We have considered a causal question already. How does changing party affiliation of the governor change the COVID-19 cases? Now let's consider a simple one, a simpler one. So we want to consider the simple question of how changing the size of the class impact the test performance of students. Let's say the students are the Hello Kitties. A causal question is as follows. How should we expect the test performance of this kitty to change if we reduce the size of her class, move all the other students, move these students to other classes, and by doing that, reduce the class size that the red kitty is in to a smaller one, reducing the size of her class from 40 to 20 without changing anything else. What's going to happen to the test performance of the red kitty? Then that is a causal question. The important thing to emphasize is there is the change and there is the no change. The causal question is for class size. The causal effect of class size is what happens when we change class size without changing anything else. Okay? Without changing anything else, including the observable and the unobservable. So that is a causal question. Now let's try to tell a story to build a causal model. One story says that test score is determined by the kitty's capacity to learn, as well as the quality of teaching. So both the learning and the teaching. So written in mathematical terms, you can write the test performance, which is Y, the test score, as a function of the learning capacity and the teaching quality, so L and T. Now, of course, there is the measurement issue. How do you measure learning capacity and how do you measure teaching quality? Suppose you can measure learning capacity by multiple dimensions of the kitty's characteristic. So we can measure learning capacity by, say, IQ, parents' level of education, as well as other relevant factors. And you can measure teaching quality by things that are related to the teaching environment, like teacher experience and class size and other things that might affect teaching quality in the classroom. So L is a function of the student characteristics, IQ, parental education, and other things. And T is a function of the teacher experience, class size, and other things. Now you put these measurements into this model that you have. And now you make it even more simple, make it simpler. Let's say Y is related to all these observables in a linear way. Okay? So assume that F is linear in these observables. And also it's separable between the observable and the unobservable. So then Y can be written as a linear function of the observables, which include class size, IQ, parental education, and teacher experience, plus a part that comes from the unobservables. These include unobservable factors on the student side as well as on the teacher side. Then this would be a causal model. Then this will be a causal model for studying the effect of class size on test score. You can increase or decrease test score, holding the student's IQ, parental education, and teacher experience and maybe other factors constant. It is reasonable to imagine doing that. It's reasonable to imagine increasing or decreasing class size, holding these other factors constant. And therefore, this beta x is the quantity that represents how that change affects y. And this beta x is the causal effect of x on y. Now we have the causal regression already built. Since these unobservables are unobserved, there is no reason to distinguish the variable and the coefficient anymore because the variable is not observable anyway. The whole thing is unknown. Therefore, we can use a random variable u to represent this unobserved part. So we write the model as y equals this linear function of the observables plus u, which now represents all the other factors, all the factors that are unobserved or observed, but you choose not to include in this equation. Now, this is a causal model for studying the effect of class size on test score. And beta x can be interpreted as the causal effect of class size on test score. And if you are changing the class size from 40 to 20, then the red kitty's test score will increase by minus 20 times beta x units, according to this causal equation. Okay? When you decrease x by 20, then y changes by minus 20 times beta x. So if you commit to the story that this is the causal equation that generates y, then minus 20 times beta x is the causal effect of reducing the class size from 40 to 20. All right, so that's how you build a causal regression. What is important to remember is that in causal regression, the error term has real-world meaning. It captures all the omitted factors that participate in the generation of y. And because it has this real-world meaning, it is not necessarily mean independent or orthogonal to the covariates. You're going to need other stories to justify those equations, or you don't have to justify those equations. Okay. Now we have talked about two purposes of the linear regression model. Remember, the third purpose of the linear regression model is forecasting. Linear regression model is a very commonly used model for forecasting. For forecasting, you simply use this function as a forecast for future values of y. And often you're going to need to put in estimated values for the beta. You use the estimated version of this equation as forecast for future values of y. And in that case, you may or may not need this to be the conditional mean. Usually you do not need this to be the conditional mean. You also do not need there to be a causal story either for forecasting. Of course, causal story could help you to come up with the factors to put in the forecasting equation. And the functional form for the conditional mean could also help you to come up with the functional form for the forecasting expression, but they are not necessary. And that is a topic actually we will not talk about in this course. In future courses, maybe this topic will be developed further. In fact, Professor Bruce Hansen teaches a forecasting class that specifically talks about forecasting, and linear model is a big part of it as well. So in this course, we will not talk about this. I will just point you to Professor Bruce Hansen's course or some other courses that do talk about forecasting. So in next videos, we will start talking about estimation of conditional mean models. We'll start with conditional mean model, the descriptive model, because that's the simplest place to start for estimation. Estimating causal models is more complicated, and we will talk about estimation of causal models after we have done estimation of conditional mean models.